recall that we talked about linear elastic behavior before, and we talked about Hooke's law, the elastic modulus, or Young's modulus, and our definitions of stress and strain. So what we want to do today is to keep going beyond this region here, which we get elastic behavior. Let's keep moving along and see what happens as we get to higher and higher stress values. All right, so as we keep going, at some point we're going to get to what's called the proportional limit. And this is the limit at which we no longer have this linear region where we define again as the elastic modulus, but in fact we start to form permanent or plastic deformation. So to the left of this point, it's all elastic. To the right of this point, it's elastic plus plastic. Okay, plastic plus elastic. So we're adding in a plastic component. But if we were to unload in this region, we would get back the elastic piece. If we were, for example, to stop here and we were to unload, this unloading would follow the slope of the elastic modulus. But notice we no longer return back to 0, but in fact we have an offset in the strain. That's our permanent deformation, our permanent increase in length of our sample. So we also have this definition of the yield strength. So most of the time what's given in problems and is tabulated is the yield strength, not the proportional limit. Okay, so the yield strength is defined by what's called a 0.2% offset rule. So the yield strength, when people say that, they mean 0.2% offset yield strength. Okay, but no one says all of that. All right. So this yield strength is defined by, on the strain axis, moving over to 0.002 in strain, right, 0.2%. And at that point, we go ahead and we draw a line with the slope of the elastic modulus. And then where that line hits our stress strain curve, that is our yield strength value. So that's the method that we would use to find that. So why do we use that and not the proportional limit? Well, the problem with the proportional limit is that it's difficult to really define where that is. So this is very idealized data, so it's fairly easy to see. If we were to put a nice straight line on the initial part, we could see where it starts to deviate and we could define this point. But many times for real data, it's very difficult to define exactly where this proportional limit is. Okay, so the 0.2% works very well. In particular, this is really true for the metals and alloys. Okay. We'll talk about the polymers when we get to that chapter. And the ceramics, we'll see that they don't have yield points. They just fracture before they would actually ever get to plastic deformation. Okay, so we use this method, this 0.2%. And although it makes it look like there's quite a difference between the proportional limit and the yield strength, in reality, there's not a big difference between these 2 points. Okay? This curve is just really exaggerated for the sake of defining these 2 values. So again, this is the one that we are going to stick with, the yield strength. Okay. In some texts, this is given sigma 0 sub 0 as the symbol instead of sigma sub y. Our text it uses sigma sub y. But if you're looking at a mechanical text, you may see sigma 0 written instead. Okay. All right. There are some stress strain curves, particularly in, or the plain carbon steels, I should say, mainly just iron and carbon and no additional alloy elements, where the curve may actually continue on up to some particular point. So this is all elastic. And then when the curve deviates from this, the stress actually drops. And then we get this, what's called serrated yielding. And then the curve would then start continuing on and behaving like the rest of most samples. We'll take a look at that apart in a minute. And if we do this 0.2% offset yield strength, we'll see that it will put us in this lower yield point region. So this upper yield point is similar to stick slip type friction cases. So the upper is kind of the stick. And then once you finally surpass that, your sample will continue to move, say in the dynamic friction case, or in this case, we're starting to move dislocations. And once we get them moving, they move at a lower stress value. So the lower yield point is the design point here, not the upper. All right, so let's keep going beyond that region. So again, here's the elastic region. So somewhere in here is a proportional limit. If we do our offset yield strength, we will probably end up pretty much the same place on this scale of the curve for the yield strength itself. If we could keep going, eventually we're going to get to a maximum value. This is referred to as the tensile strength or the ultimate strength. Sigma ultimate, that's typically in mechanics books. Tensile strength is usually used in materials books. And at that point, the curve will start to fall off, and then eventually we get fracture. All right, so what's happening at the maximum here is that this is the point at which the diameter of the sample undergoes an instability and starts to neck. And once it starts to neck and shrink in this one location, then all of the strain, the plastic deformation, gets confined in that region, and then we eventually have a failure. I'll post this video in Canvas for you, and we can see this copper rod being pulled. And then as it's going, you'll see that it necks down and then eventually fails. Okay. Hopefully you also saw that when you watched the tensile video for the stainless steel sample. You saw that necking behavior and then eventually the failure. If we take a look at samples that have failed in a tension test, you can see two main kinds of behaviors here. One is where the cross-sectional area, the diameter here, you can clearly see has decreased, right? And another case where it looks like there's no change and we just have a flat fracture. This one that's decreased also seems to have this shear lip on it. This kind of looks like a cup. There's kind of the bottom of the cup and the shear lip. And this one is more like a cone. It's a cup and cone fracture. Okay, this is a shear fracture. This is a brittle fracture. Okay, shear fracture and a brittle fracture. So the ductile sample will have a lot of change in this cross-sectional area. Go ahead and take a look at the full curve again, and we'll just point out a couple of properties that we can get off of this. So again, this initial region, if we have the full set of data, what we're going to have to do is replot it. And we're going to need to replot that so that we can actually measure the slope here in this initial region. Okay, to get the elastic modulus that's shown here. We're going to need to be able to see this 0.002 to do our offset. Remember, this is the same slope. And then where it hits our curve, that is our yield strength. Then we use the full curve to define the tensile strength or ultimate strength of the sample, and ultimately the strain at fracture. So this could be related to the ductility of the sample, the percent elongation at fracture, in this case being 37%. This is referred to here as fake data. This means idealized or schematic data. I'm going to show you real data in a next video. So again, summary, we can get the elastic modulus from that linear region. We can get the strength, and there's two types. There's the yield strength, and then there's the ultimate strength or tensile strength. Okay, so when one says the strength of a sample, you can already see that you have to be careful because there's two different types, right? The yield strength here, defining when we go plastic, and then the tensile strength being that ultimate load that the sample can withstand before it starts necking and final failure. The ductility can be defined in terms of that percent elongation at failure. Right? So we just saw a case for 37%. The ductility could also be measured in terms of a percent reduction in area. Okay, so how much did the sample change in cross-sectional area? So that's a measure of ductility. So we can actually put some numbers to ductility now, instead of just referring to a sample as being ductile or not ductile. If we take a look at the material properties, so we have here structure insensitive properties. This is the elastic modulus, the density of the sample, the melting point. So these things are all material properties, and they're relatively insensitive to any kind of structural changes. So it doesn't matter how many dislocations I have in my sample. For example, my elastic properties will not change. So the yield strength, the tensile strength, and things like ductility, these will all change with the number of dislocations in my sample, maybe the size of grains in my sample. So those would be structure sensitive properties. Okay. They're still material properties.